Welcome everyone to the next Gen 4 International Forum webinar presentation. Today's presentation's on materials challenges for Generation 4 reactors. Doing today's introduction is Dr. Patricia Pavier. Patricia is the Director of the Office of Materials and Chemical Technologies within the DOE Office of, sorry Patricia, your signature is a little wrong. I butchered that a little bit.
That's fine.
But
nuclear energy.
Yeah, nuclear energy.
Okay, thank you so much, Bertha, for the introduction. It's my pleasure today to have Dr. Stu Malloy from the Los Alamos National Laboratory. He's a team leader for MSTA, the Materials at Radiation and Dynamic Extremes. He has worked at Los Alamos for 28 years, and he is the Advanced Reactor Core Materials Technical Leader for the Nuclear Technology Research and Development's Advanced Fuel Campaign and the NEET Reactor Materials Technical Lead for the DOE Office of Nuclear Energy. He earned his PhD in 1994 in Material Science from Case Western Reserve University and is a registered PE in metallurgy. He has applied his expertise to characterizing and testing different materials and ceramics in extreme environments. He has also more than 190 peer-reviewed technical publications and numerous presentations. And without any delay, I'm going to give the floor to Stu. Thank you again, Stu, for volunteering to give this GIF webinar.
Well, thank you, Patricia, for that very nice introduction. It's a pleasure to be here, and welcome everybody. Good morning, afternoon, or evening from wherever you are hooking in from. Let me just start off with a brief outline of what I'll talk about today. I'll give a little background on radiation effects in materials, and then talk about radiation effects in specific materials for nuclear reactors, specifically face-centered cubic and body-centered cubic alloys. And then I'll get into the specific Gen 4 reactors and their materials and challenges for the different operating conditions of these reactors. In the end, I'll summarize that and then summarize some of the performance issues. So I think most people here know that materials in nuclear systems can fail, especially in some of the harsh conditions that they must see. For example, in the upper left-hand, well, I'll use a poet. In the upper left-hand corner, the fast reactor ducts that saw very high exposure, you can see up to 52 to 34 dPa exposure, actually failed when removing them from the reactor. That's a high-dose reactor issue. And then other issues from corrosion, as you can see from the Davis-Besse reactor vessel head degradation or grid-to-rod fretting in typical zircaloy-clad fuel cladding, and crud as well can be an issue as well. So clearly there are some materials issues you can run into in reactor systems. What I want to do is just summarize the basics of radiation damage. Most people know when a high-energy particle comes into a material, into a metal lattice, when it interacts with that, it can form a large displacement spike, as you can see shown here. That's just picoseconds after the actual interaction with the material. But then afterwards, when it relaxes, you end up with a large number of interstitials you can see around the displacement spike, and vacancies around the center. And that's what leads to damage within the material that can cause changes in mechanical properties with high-dose radiation. So in summary, I mean, you can separate this into two things that happen during radiation damage. You can have transmutation occur, so you can actually activate the material, of course, and also you can produce new elements within the alloy. And many times, such as, for example, in nickel transmutation, during that decay of the nickel 58 atom, you can give off alpha or helium into the material, which can then lead to other deleterious effects in the material. And then the second change are the material's property changes due to atomic displacement. As I pointed out just before, when a high energy particle comes in, it can lead to displacements which cause vacancies in the material, and then the atom goes into an interstitial and then causes self-interstitials in the material as well. And those vacancies can collect to form voids in the material, which leads to swelling. You can get also, because of the high amounts of defects in the material, you can get increased diffusivity, which leads to local segregation. And then you can even precipitate out new phases or cause amorphization of phases under radiation. So all these can lead to significant property changes in materials under radiation. An example that most people can sort of think of with respect to a high energy cascade coming into the material is think about playing pool, and when the initial cue ball hits your set of pool balls, which would be like your atoms in the lattice, it causes displacements as the energy is transferred from the initial high energy neutron or scattered neutron to the actual particles within the lattice, and then that creates a cascade of defects, including vacancies and interstitials within the material. And what's important in the end really is the ultimate fate of the point defects. So as shown here, you have the initial event of the particle interacting with atoms in the material and causing vacancies and self-interstitials. Now, depending on where the vacancies and interstitials are, you can get some recombination. Also, depending on the temperature, you can get recombination, which then that's really not an issue, but then you can also run into clustering, which can lead to voids in the material, or in some cases you can get absorption of the vacancies or interstitials at sinks. And that can lead to increased segregation, which can affect mechanical properties in the end as well. And as shown here down below, you can see right after that initial cascade, you have a very large number of defects within the material, but only a small time later, it's the recombination of those defects and what's left that actually causes the changes in mechanical properties. So that's really what we're worried about in looking at how a material can withstand high-dose radiation in a reactor application. And so this slide just shows that when you sort of step up in scale, the actual changes in properties happen at the mesoscale. So you have different self-interstitials and different atoms perhaps made under radiation, which then lead to dislocations within the material, which can at a larger scale lead to interactions with buildup of defects at grain boundaries or different phases that can precipitate out under radiation. So all of those are eventually what you're worried about with changes in mechanical properties in the material. So what are typical alloy compositions? Just as a background, before I get into talking about the different material changes, austenitic stainless steels are used in many different applications within reactors. So that's 316L and 304L are high chrome, high nickel alloys, or Inconel 718, which is a high nickel, also chrome alloy, and alloy 600, also a very high nickel alloy. So these are all austenitic or face-centered cubic alloys. Ferritic steels, which also have significant applications to nuclear reactor components, have a body-centered cubic crystal structure, and typical alloys are those such as modified 9-chrome 1-moly, which is a high chrome, but you can see there's no nickel in the alloy, so you stabilize That way you don't stabilize the austenitic phase, and it's a fully ferritic alloy. And HT9 as well has higher chrome than modified 9-chrome 1-moly, but also about 0.2% carbon. And that's how you get a ferritic martensitic microstructure within those materials. And then zirconium alloys, of course, are also typically used as cladding materials in thermal reactors because of its low thermal neutron cross-section. So those are typical materials. To summarize radiation effects in metals, as I already sort of pointed out, typically what happens in metals is you get basically Frankel defects, self-interstitials, and vacancies, and these are sort of on the right are diagrams of a body-centered cubic unit cell and a face-centered cubic unit cell, and the close-packed slip planes are these boxes and triangles that are shown here. They don't have any charge compensating defects. There's little effect from gamma radiation, and amorphization is typically uncommon, unlike what you can see with a ceramic material. The close-packed structures are the face-centered cubic, the body-centered cubic, and then with zircaloy, for example, there's a hexagonal close-packed material. A very nice paper by Zinkel and Gonim shows a way to understand radiation effects in different materials over a class of different alloys, BCC alloys and FCC alloys, and you can sort of look at them based on their melting temperature. And what I'm going to center on in the next slides are at lower temperature region where vacancies are immobile and interstitials are mobile, resulting in interstitial clusters and loops and small vacancy clusters that are formed within the material and results in significant hardening, and can also result in reduction in ductility. At medium temperature, which I won't talk about much in my talk, but the medium temperature, which is typically the operating temperature that you'd like to use these materials, you have increased vacancy mobility, and it results in more self-annihilation of defects. So you get more recombination of defects, and so you get less hardening in that region. But at high doses, you can run into void swelling in those areas as well. And at higher temperature, you can run into issues such as with increased mobility in the material, you can run into issues such as creep, or if helium is formed, it can lead to helium embrittlement because it's now able to diffuse to grain boundaries. So that's one way to think of how mechanical properties are affected in these different classes of alloys. So I'm going to center on 3 different alloy classes that I'll talk about: 316L and 304L stainless steel, face-centered cubic alloy, alloy 718, also face-centered cubic, and then some ferritic steels and their exposure to radiation. So like I said, I'm centering at lower temperature at 50 to 200 degrees C in 316L and 304L. So typically what you see under radiation in these TEM micrographs shown here is a buildup of interstitial clusters, which eventually form interstitial loops with dose. And you can see that from at 0.7, a fairly low dose DPA, there's a small number of loops within the material. At 3.8, you can see a much higher density, and at 9.8, you can see that the loop size is actually starting to grow a little bit as well. And to summarize that here, the calculations done on this irradiated material show that the loop density starts at about 10 to the 22 per meter cubed, goes up to about 5 times 10 to the 22, and then it actually starts to go back down. And at that point, like I was saying before, the mean loop diameter is starting to increase. So between 0.7 and 3.8, you actually start to saturate the whole the dislocation density within the material, and you can see that number actually is pretty flat from 3.8 to 9.8 dPa, while the diameter is going up, the loop density is going down, keeping the overall total dislocation density about the same. And how does that affect mechanical properties? This can be shown here in tensile curves versus irradiation dose. So initial unirradiated material has a very high ductility, up to almost 40% uniform elongation. And then after a very low dose, just 0.09 dPa, you can already see hardening in the material. At 1.1, it's continuing to harden. At 2.9, it goes up even further. So now you've gone from about 300 MPa up to about 800 MPa increase in yield stress, and uniform elongation is starting to reduce significantly. And that is the point where you've got sort of saturated the microstructure with defects, and from there it sort of gradually increases in yield with increasing dose, as shown as a change between 2.9 and 9.3 dPa. That can be summarized, well, one of the reasons why you run into significant reduction in ductility is because the microstructure has a large number of defects in it, as shown in this image here. And when one set of dislocations starts to go through that microstructure, it makes a channel. So it makes a dislocation channel in that microstructure, and that leads to a large load drop in the stress-strain curve. So as you try to deform this microstructure, you get significant localized deformation, which reduces the uniform elongation, as shown in these curves here. And at the same point, you can also summarize the change in mechanical properties with dose in this graph right here as well. Yield stress, as pointed out, increases significantly after sort of very low dose irradiation. I mean, it actually started down here at around 300. It goes up very, very fast initially, and then it sort of plateaus and increases with dose all the way out to, in this case, tested out to about 10 dPa. And along with that, reading this on the right-hand side, uniform elongation drops significantly immediately. So it goes from 50 to 60% down to about 20%, and then it continues to decrease with increasing dose to a point around 4 to 5 dPa. The uniform elongation looks like it's 0, but it's about 1% here, all the way out to even high dose. And interestingly enough, even though the uniform elongation looks very low, this material is still failing in a ductile manner. So this SEM image shows a typical ductile fracture on the surface, but because it's so localized, the deformation is so localized, you end up with very low uniform elongation in the material. Now, Inconel 718, also a face-centered cubic material, its response to radiation is a little bit different. This material has, as shown here, has a large number of precipitates within the material which give it a very high yield strength. So it has gamma prime and gamma double prime precipitates within the material. They are very fine distribution of precipitates in the range of about 10 nanometer in size, and they result in a very high yield strength material. But after only 0.6 dPa, all of these gamma prime and gamma double prime precipitates, when irradiated at low temperature, go into solution, and with increasing dose, they stay disordered all the way out to 13.1 dPa. If you look at the plot of how that affects the yield stress or the stress-strain curve, it's a bit different than what we saw in the austenitic 316L stainless steel. In this case, you start off with a very high-strength material. Its yield stress is a little over 1,000 MPa. Has fairly good uniform elongation, up to about 16-17%. But after only half of a dPa, when the precipitates become disordered, the uniform elongation decreases significantly. You get a little bit of an increase in yield stress because you are putting a large number of defects, interstitials and vacancies within the material. But with increasing dose, as you continue to cause the precipitates to go into solution, the yield stress actually goes down. So from 0.5 to 1.2 to 4.2 dPa, the yield stress is actually going down in the material. And you can actually see that here in a plot of yield stress on the left-hand side. That's the black dots. It increases initially, but then with increasing dose, it actually decreases out to about 11 dPa. And at the same point, there's an abrupt reduction in uniform elongation, which is shown here, to a low amount, but once again, it's still failing in a ductile manner, at least right now. The uniform elongation is around 1% in that material. And how does the fracture surface change with irradiation? In this case, we've even tested, this was actually a component that was tested here at out to 20 dPa, that's shown here, or 19.8 dPa. But in these these fracture surfaces, you see fairly ductile fracture at 0 dPa. You see ductile fracture at 4.6, but at 10.5 dPa, you see some areas, as shown here, of flat or brittle type fracture, but most of the fracture is still ductile fracture in that material. But then at 19.8 dPa, there's an abrupt change. And in this case, I didn't show the stress strain curve, but this material is actually breaking in the elastic regime and showing intergranular fracture. So in summary, going back to the diagram that I showed before, how do we find materials that can actually reach very high doses, for example, above 200 dPa? If you look at these classes of alloys, the refractory alloys are difficult to go to very high doses because they run into embrittlement issues due to interstitial pickup or swelling or specifically irradiation hardening. FCC alloys look good, but they run into issues because of void swelling after about 50 to 60 dPa, as well as segregation. Zircaloy has issues with hydrogen embrittlement, so really what that leaves are the ODS ferritic and ferritic martensitic steels, which I'll talk about here in the next couple of slides. So here I want to summarize radiation effects in modified 9-chrome-1 moly, and I'll talk about some oxide dispersion strength in ferritic alloys as well in the end. So modified 9-chrome-1 moly at low temperatures looks, in a sense, somewhat similar to the changes that we saw in, for example, 316L stainless steel, although it starts off with a much lower uniform elongation. In this case, it's only about 5 to 6% uniform elongation. Now, these stress strain curves are a little bit confusing to look at because I've got two different test temperatures at 160 and 50 degrees C, which causes a slight difference in the stress strain response. But in general, at low dose, 0.05 dPa, you still see about 4.5% uniform elongation. But at 0.9 dPa now, it's dropped fairly precipitously to around 1% uniform elongation, and it stays like that at 2.9. This is a different irradiation temperature, so it looks a little bit lower. But if we were at the same irradiation, it would be going up in yield stress, and then it continues to go up in yield stress all the way out to 8.8 dPa, with maintaining a fairly low uniform elongation. And that's also summarized here again. Yield stress shown on the left-hand side in the filled squares increases significantly after fairly low dose, and then it sort of is a fairly gradual increase with increasing dose out to 10 dPa. And at the same time, uniform elongation is dropping off fairly quickly out to fairly high dose, out to 10 dPa. What goes along with that is in body-centered cubic alloys, you have a ductile to brittle, or DBTT, a ductile to brittle transition temperature. As you start to harden that material with low temperature radiation, it causes the ductile to brittle transition temperature to increase. In this case, it's going from about minus 150 out to at 9.3 dPa, almost to room temperature. So that can be an issue with low temperature irradiation of these materials. And some work that we did here at led out of Los Alamos was analysis of a ACO3 duct that was made out of HT9. So in this case, we were able to look at a component. What we did was to take advantage of the fact that along the duct, the irradiation temperature goes from, right here on the right-hand side, it goes from about 380 degrees C out to about 500 degrees C as you go along the length of the duct. And the area where the fuel is the highest dose. And so the dose at that point, right on the left-hand side, goes from about 20 dPa out to a maximum of 155 dPa. So this was in the reactor for almost 7 years. And then as you move along the length of the duct and you move away from the fuel, the dose goes back down to even close to 0 dPa at the upper part of that duct. So we took advantage of that change in those different conditions along the duct and then cut it along different locations listed here as 1, 2, 3, 4, 5, and then use those locations to test the change in mechanical properties with irradiation temperature and dose. So in the shown here, you can see the changes in the stress strain curves with the radiation temperature, and in the upper left-hand part are the lower temperature irradiated areas. So I don't know if you can see this too well, but it's about 410 C and then about 370 and about 380 and 370 degrees C. So as you're decreasing in irradiation temperature, you get an increase in yield stress, and that's actually shown here. You plot yield stress versus radiation temperature. At the lowest radiation temperature, you saw the largest increase in yield stress over the control material. And at the same time, as shown in the other alloys, at the lower temperature, that increase in yield stress results in a decrease in the fracture toughness, as shown in these green dots here. And it also results in, as you plot irradiation temperature versus transition or ductile to brittle transition temperature, the DBTT is going up, and with decreased temperature, you get an increase in the ductile to brittle transition temperature. But I mean, I should point out that in this temperature range here at 450 degrees C, this is the highest dose area of the duct. I mean, this is 155 dPa irradiation, and there's fairly little change in the transition temperature and also fairly little change in the yield stress. So if you pick the right irradiation temperature, you can maintain the properties in the material quite well. And in summary as well, what's leading to these changes in properties are at low temperature, a high density of interstitials and vacancies. At intermediate temperature, there's a little bit of void swelling and some precipitation, but not enough to cause significant changes in mechanical properties. And at even higher temperature, there's little change in properties as well. But there is a class of materials that also shows promise as advanced radiation tolerant materials. These are called nanostructured ferritic alloys, or also called oxide dispersion strengthened alloys. And in the collaboration between UC Santa Barbara and Oak Ridge and Lannell, we've produced some of these alloys. They have a fine distribution of oxide particles, nano features, Y2Ti207 and Y2Ti05. It's made by mechanical alloying, and then as you develop this fine microstructure, that leads to the particles, which are shown here in this APT image that shows a fine distribution of oxide particles within the material. These serve as sinks for defects, and they also serve as they help increase the strength at high temperature, giving it increased creep resistance as well as increased strength at high temperature. So that could help us. You can see actually in an older oxide dispersion strengthened alloy, Ma957, that was tested in the advanced test reactor after irradiation to only 6 dPa, where I previously showed you on a ferritic martensitic steel like T91, where the uniform elongation is dropping to less than 1%. In these alloys, is less hardening. You can see it only went from 1,000 to 1,200 MPa, and the uniform elongation is still above 5% in this oxide dispersion strengthened alloy. So that may give us promise for materials for high dose applications. So now I'd like to shift gears a little bit and talk to you about the different reactors and their different reactor conditions and how that affects material performance. I'll talk initially about boiling water or light water reactors just as a background, and then get into the different Gen 4 reactor types, the thermal reactors as well as the fast reactors. So the one that most people are familiar with that produce most of the nuclear power in the world are pressurized water reactors and boiling water reactors. Their purpose, of course, is power production, and the conditions, these are cooled by water, so they're at fairly low temperature, 288 to 360 degrees C, and they have mostly a thermal spectrum, but they do have a fast neutron spectrum as well that produces displacement damage in the material at a rate of about 2 to 4 dPa per year. Some of the issues that they run into that result in having to, say, replace the fuel or other things are fuel-clad chemical interaction, hydride formation within the cladding, and corrosion of the zircaloy cladding, as well as some issues of stress corrosion cracking or irradiation-assisted stress corrosion cracking on the piping. And with the pressure vessel, as they try and push the overall age of the reactors to 40 to 60 years, they can run into aging effects for the pressure vessel as well. And sort of in comparison, the materials that they typically look at for light water reactors are different, but there are some similarities. But from what we're proposing for the sodium-cooled fast reactor or the different other gas fast or very high temperature reactor for these Gen 4 concepts. So the coolant, of course, is different. In the light water reactor, it's water. In the sodium fast reactor, it's sodium. And then in the high temperature reactor, it's helium. And the materials vary from, for cladding, they're proposing 9 to 12 chrome steels, although most sodium fast reactors use austenitic alloys, but they're looking at changing to ferritic steels for cladding. And then in the very high temperature reactor, 6-6 composites are one of the prototypic alloys. And the core internals actually have some similarities. 316 stainless steel is used in sodium fast reactors, and it's also used in some parts of gas fast reactors. And in the high temperature areas, alloy 800H needs to be used for better high temperature strength. And then in the heat exchanger, in a light water reactor, they have nickel-based superalloys, but 9 to 12 chrome stainless steels are proposed in a sodium fast reactor, and alloy 617 in a high temperature gas fast reactor. So despite the differences in operating parameters, there are some similarities across the different reactor concepts and specific areas where they're looking at more advanced alloys as well. So now let me get into the different Gen 4 reactor concepts. The very high temperature reactor is a thermal-based reactor. Its purpose is more efficient power production by running at a higher temperature, and it also has some inherent passive safety features. In this case, the coolant is helium. The temperature is very high, can be up to 950 C outlet temperature. And for that reason, it uses a solid graphite black core. And since it's a thermal-based reactor, its buildup in dose is about 2 to 4 dPa per year. But the materials issues relate to improved metallic materials for the very high temperature reactor pressure vessel, and as well as improvements in graphite properties, improvements in the high temperature mechanical properties of the coolant piping. Inconel 617 is the proposed material in that area, and development of better materials for the intermediate heat exchanger. The supercritical water reactor, also generally looked at as a thermal reactor, there is a fast spectrum concept as well. This is also proposed for more efficient power production. In this case, you're using supercritical water coolant, and so the outlet temperature is fairly high at 550 degrees C. Doses can be up to greater than, pressure can be up to greater than 20 MPa to make it supercritical water. And also the doses, since in the thermal reactor concept, are 2 to 4 dPa per year. Because of the higher temperature and the higher pressure, there are issues related to corrosion and stress corrosion cracking. Radiolysis and water chemistry can lead to increased corrosion of material. Worrying about dimensional and microstructural stability at these higher pressures, and embrittlement and creep resistance of cladding at the higher temperatures that we're running at in this supercritical water reactor. As you know, the temperature range can range from 280 up to 620 degrees C, and the radiation damage dose can range from 10 to 30 dPa in the thermal spectrum, but the fast spectrum can be even higher, up to 100 to 150 dPa. Now let me summarize some of the fast reactor concepts and the materials challenges there. Why look at fast reactors? Well, one of the advantages are that fast reactors can address the back end of the fuel cycle. So we could, in a fast reactor, separate out the long-lived isotopes and make a new fuel to irradiate in the fast reactor, provide power with that new fuel, and also reduce the lifetime of, or reduce the need for having to store the waste in the reactor for as long a period of time as you can sort of see in this graph here. So in the LWR once through cycle, you can see an increase in heavy metal mass with irradiation will build up significantly, but if you can add a fast reactor to that, you can reduce that heavy metal mass by, in a sense, separating out those isotopes and using that as fuel in the reactor. So what are the different different fast reactor concepts? I've sort of put these two together, the sodium-cooled fast reactor and the lead fast reactor. In both cases, we're looking at one of the purposes is high-level nuclear waste transmutation and increased power production, and used for power production, as well as using it for actinide management. The coolant can either be sodium, pure lead, or lead bismuth. And with the pure lead concept, the outlet temperature is going to be higher, up to even 800 degrees C, whereas the sodium or lead bismuth concepts, the outlet temperature is about 550 degrees C. Because it's a fast reactor, the total dose can build up at about 20 to 30 dPa per year, and that leads to high dose radiation effects in core, as well as especially in the lead case, you can run into liquid metal or lead corrosion of materials. But this is, of the fast reactor concepts, especially the sodium fast reactor concept is the more commonly used fast reactor around the world. This is actually a picture of the FFTF research reactor, which ran from 1980 to 1993 in Hanford, Washington. The gas-cooled fast reactor is a concept that runs at even higher temperature. It's also for high-level nuclear waste transmutation, more efficient power production, and actinide management. In this case, the coolant would be helium or supercritical CO2, and it has a fairly high 850 C outlet temperature. There are a range of different fuel options and core configurations, but because it's a fast spectrum, the dose will build up significantly at 20 to 30 dPa per year. The materials issues are right now, because of the very high temperature and the high dose, fuel development is one of the major issues. You need to achieve a high power density and be able to retain fission gases at high burnup and high temperatures. One of the proposed fuels is a ceramic or a Sur fuel, and others have coated actinide carbide sort of kernels of fuel within the material. And there also are some alternative fuel concepts as well. Fuel particles with large kernels and thin coatings and ceramic clad solid solutions. So there's a large amount of research that needs to be done on fuel development in this area, but it could have advantages with the much higher temperature and the more efficient power production. And then the third concept is a molten salt reactor. In this case, there is a thermal and a fast reactor concept. The purpose is high-level nuclear waste transmutation is one of them. It also would give you fast reactor power, and you can either, there are different concepts. There's a liquid fuel core, but there also is a solid core with a molten salt coolant as a concept as well. So the fuel could either be liquid sodium fluorides or chlorides. The fluoride-based fuel is the fast reactor concept. The chloride-based fuel is typically the thermal reactor concept. Temperature can be up to 700 to 800 C outlet temperature. The core materials to give it the corrosion resistance are typically nickel-based alloys. And in the case of the solid fuel, it's generally thought of as a silicon carbide-based solid fuel, but that isn't. There are different options out there. But one of the advantages is it does run at low pressure as well, less than a half an MPa. But in the case of a fast reactor concept, the displacement damage is high, 20 to 30 dPa per year. So there are some significant materials issues, materials compatibility that you would need to do in maybe a controlled chemistry test loop, radiation damage to the pressure vessel and coolant piping, and materials compatibility under irradiation. So there is more research that's needed in these areas as well. So let me summarize the reactor operating conditions here, and fusion energy is also listed here as in comparison. But the fast reactors are listed up above. The lead fast and sodium fast reactor are at fuel temperature. That's the cladding temperature at 500 to 600 C. And lifetime doses are fairly high. There you want to push the dose to 150 to 200. In some cases, there's some concepts looking at pushing doses even up to 400 or 500 dPa. In the Gen 4 gas-cooled reactor, then the fuel temperature is much higher, up to 2,000 degrees C. It's helium-cooled. Nickel superalloys are the typical structural materials, with some areas where ceramic composites may be used, and structural temperatures can range from 500 out to 1,200 degrees C. As you then move over to the thermal reactor concepts, here's your typical light water reactor. Its coolant is water, temperature 200 or 280 to 350 degrees C. The very high temperature reactor is much higher in radiation temperature, but since it's a thermal reactor, the approximate dose is maybe about 10 dPa, and the temperature is fairly high in the core. Supercritical water reactor is a UO2 fuel. Its fuel temperature of 800 to 2,000 degrees C, and that's in the center of the fuel. But the structural temperatures are higher than a light water reactor at 300, even up to 600 degrees C. And then finally, the last concept, the molten salt reactor, would either have fluorides or chlorides for the fuel. It could even have a solid fuel with a molten salt coolant. Fuel temperature of 700 to 800 C. Nickel-based alloys are the primary structural materials, but others are being looked at. And in the fast reactor concept, the dose can be very high, out to 100 to 150 dPa. So all these can lead to different performance issues that I've sort of summarized here, from issues for light water reactors to the thermal, or the very high temperature reactor, and the supercritical water reactor, where helium embrittlement or creep strength can be an issue, and swelling could be an issue at high temperatures. And summarizing the issues for sodium fast reactor, the sodium fast reactor compared to the lead fast reactor, the issues are fairly similar, except for the lead fast reactor has increased corrosion from the lead coolant. And all the way, I guess, to the bottom, the molten salt reactor, typical issues are corrosion, of course, with the coolant, helium embrittlement in higher temperatures, creep strength at higher temperatures, radiation-induced segregation, transmutation, toughness, and oxidation. So it's all summarized here. And with that, I would be happy to take any questions after perhaps a few comments, I believe, from Patricia. So thank you.
Thank you, Dr. Malloy. If you have questions for Dr. Malloy on this presentation, go ahead and type those into the chat pod now. And while those questions are coming in, we'll just take a look at the upcoming webinar presentations. We have presentations scheduled in March from Professor Abderham from Belgium on SCK-CEN's R&D on Mira. In April, Russia BN 600 and BN 800 will be presented by Dr. Ashurko from Russia. And in May, a presentation on proliferation and resistance of Gen 4 systems by Dr. Barry with Brookhaven National Laboratory.
Yeah, thank you, Bertha, and thank you so much, Sue, for the excellent presentation. I would like to remind the audience of a GIF symposium in Paris in October 2018. If you want to have some information on this symposium, we put the website. The abstract deadline has been extended to the 31st of March. I encourage the professor to allow some PhD students to participate to this symposium, and also companies to encourage their young staff and professionals to come and present their work. So with that, thank you very much, and I think we will see the questions that you have for Sue.